Hi, everyone. By the way, after this video, you should be able to do the first two problems on lesson 28. So you can finish the homework up through lesson 28, homework problem number 2. Okay, so back to lesson 28, estimating a population mean mu in case sigma, the population standard deviation, is assumed known. Again, that might seem like a strange assumption, but let's start with that. And furthermore, we're going to assume that the central limit theorem applies. So make sure that the CLT applies if we're applying these methods, meaning that either the Big Daddy distribution is normal or the sample size is large enough, bigger than 30, say. All right. Now our formula for a 1 minus alpha confidence interval for mu, 1 minus alpha, it could be something like 0.95, 0.99, for example. All right, that's a confidence level. The formula for the confidence interval takes on this form. The population mean mu, we believe it can be the sample mean x bar, give or take the margin of error e. Again, we're using plus or minus differently from, say, the quadratic formula in algebra. The idea is that we believe that the population mean is within e units of the sample mean. Now, the margin of error is obtained by this formula, which is the positive critical value times the standard error of the x-bar distribution. So this all kind of makes sense. To get the limits of the confidence interval, which are obtained by taking the plus case and the minus case in this formula, to get the confidence limits, the limits of the confidence interval, you start at the sample mean and you walk z standard errors away, where the z-score here is the positive critical value. The confidence level has a direct impact on what this positive critical value is. The margin of error, by the way, is always positive. All right. To be conservative, round up the margin of error and use the same number of decimal places as the given value for x bar, the sample mean. All right. Example 1. Let's apply these ideas. We're going to develop a 95% confidence interval, CI, for a population mean mu. And we're going to assume that the population standard deviation is known. So here's an example of where that could happen. Let's say a machine is designed to make cartons of 16.0 fluid ounces of ice cream. The amount of ice cream in the cartons is approximately normally distributed with population standard deviation 2.35 fluid ounces. And we're assuming this is the population standard dev, sigma. So this is going to be a kind of calibration problem. We're going to assume that the machine always exhibits the same amount of variability among the cartons of ice cream that it produces. However, we're wondering if the machine needs to be recalibrated, in the sense that we're wondering if the machine might be producing too much ice cream to put in the cartons, or maybe it's putting too little ice cream in these cartons. These cartons are labeled 16.0 fluid ounces. So if they're going to be honest, if they're going to have that balance between satisfying the consumer on the one hand and making their profits legitimately on the other hand, they want to make sure these cartons are averaging pretty much 16.0 fluid ounces. Also, truth in advertising. They want the label to be accurate so they don't get either sued or maybe they'll get in trouble with the government. All right. Or the Better Business Bureau. Okay. So let's say the ice cream company wants to know, does this machine need to be recalibrated? Okay, are we concerned that the machine is putting too much ice cream, too little ice cream? We're assuming that the variation is the same, but we're wondering if the machine is putting too much or too little ice cream in the cartons on average. So the company hires some people, some statisticians, and they take a random sample of 19 cartons. The sample size, little n, is 19. We don't care about big N. Big N could be in the thousands or millions, but it's going to be way larger than little n. So we can assume independence and all that. The sample mean, let's say, for these 19 cartons is 17.2 fluid ounces. So you could imagine an Excel spreadsheet with 19 entries where they input how much ice cream is in each carton for these 19 cartons, and you can get the sample mean for these 19 cartons. How much ice cream is in these 19 cartons on average, and we get 17.2 fluid ounces. That's our value for X bar. I hope you know that. All right. Find a 95% confidence interval. 95% is our standard confidence level. For the population mean mu, right? The population mean amount of ice cream per carton. So we want a 95% confidence interval for mu, where mu is the population mean amount of ice cream per carton. Okay, so we're going to write the confidence interval, the CI, in two forms. One is in this form. I'll put this in blue. We're going to say that the confidence interval for mu is going to consist of the sample mean, give or take a margin of error, E. We're also going to write this confidence interval in the form lower limit, comma, upper limit, inside parentheses, or even brackets. Once we get the confidence interval in this form, we can take the minus case and the plus case, and we can figure out the lower limit and the upper limit. So once we get this form over here and get the values here, then we can figure out the lower limit and the upper limit for the CI. Finally, let's interpret the confidence interval, the CI, using proper English. As a hint, you could get this from software, like Excel, we're going to use the fact that 95% of the Z distribution will lie between these two critical values, negative 1.96 and positive 1.96. In other words, since we're going to use the Z distribution here, to get a 95% confidence interval, we're going to need these two critical values, which always correspond to a 95% confidence level when Z is involved. So let's do it. We're going to find the confidence interval, write it in these two forms, and interpret it. Let's do it. Okay. First off, just as a shorthand here, let mu be all of this, the population mean amount of ice cream per carton. Ideally, you would write that out. And why do the methods of this lesson apply? What assumptions are holding? Well, we're finding a CI for mu and not P or sigma or something else. We're finding a confidence interval for a population mean mu. We're assuming that the population standard deviation sigma is known. We're assuming sigma is known, 2.35 fluid ounces, because the company is taking that for granted. They think that the population mean might be different from 16.0 fluid ounces. Maybe that changes over time potentially, but they're assuming that sigma stays the same. It's a calibration problem. We're assuming also that the ice cream amounts per carton are approximately normally distributed. Okay, we assumed a normal distribution for the Big Daddy distribution. Therefore, what theorem applies? The central limit theorem for means. Okay. Our cast of characters, our sample size, little n, is 19 cartons. The sample mean, X bar, the average amount of ice cream per carton among the 19 cartons was X bar, 17.2 fluid ounces. Maybe you get that from your Excel spreadsheet. We assumed that the population standard dev, sigma, was 2.35 fluid ounces. That was given in the problem. So let's find the margin of error. Okay, so that's where these formulas come in. That's where these formulas come in. And I'll give these formulas on an exam. Okay, here's the formula for the margin of error. It's this positive critical value times the standard error, sigma over root n, from the CLT. All right. Again, the critical values are going to come from our hint. 1.96 is our positive critical value, z sub alpha over 2, or half alpha. All right. The margin of error is given by the positive critical value, 1.96, for a 95% confidence interval. Again, for a 99% confidence interval, as we'll see, this will be bigger. It's going to be 2.58. And then the standard error, it's sigma over root n, 2.35 over the square root of 19. Work this all out. Be careful, but work this all out. If we round off to 1 decimal place, we get 1.1 fluid ounces. Now, 2 comments. First of all, we're rounding off to 1 decimal place because the sample mean, it appears, was also rounded off to 1 decimal place. Now, if you wanted to be conservative, then you would actually round up. I forgot what you get when you round up. It could be 1.1 or 1.2, but bear in mind that you could round up. So if the margin of error on your calculator turns out to be 1.13, let's say, by the argument of being conservative to play it safe, you could round up 1.13 up to 1.2, and I'd accept that. You're being conservative in that case. Anyway, we're going to say the margin of error is 1.1 fluid ounces. So our 95% confidence interval for mu, the population mean amount of ice cream in each carton, if you consider all the cartons produced by this machine, at least nowadays, okay, is given by this. The confidence interval for mu is given by the sample mean x bar, give or take e, the margin of error. X bar is 17.2. The margin of error is 1.1. Notice they have the same unit. It's fluid ounces for both the sample mean and the margin of error. Okay, and we've answered part of the problem. Okay. We have found our 95% confidence interval in this form here. Mu equals x bar plus or minus e. We found the form and we found the appropriate values for x bar and e. And then, just by taking the 2 cases and separating them, you can find the lower limit and the upper limit. Remember, the lower limit corresponds to the minus case. Be careful. Okay, it's always going to correspond to the minus case. 17.2 minus 1.1. That's going to be about 16.1 fluid ounces. The upper limit, that's when you take the plus case. Okay, 17.2 plus 1.1. Whoops, that should be a plus sign there. Plus 1.1, and that's about 18.3 fluid ounces. So our 95% confidence interval for mu, in this form, where we indicate the limits, it's from 16.1 fluid ounces to 18.3 fluid ounces. Technically, you should put units. And remember, the lower limit is obtained from the minus case here. The upper limit is obtained from the plus case here. If for some reason you find it easier to work out the upper limit first, that's fine, but make sure to put the upper limit to the right. Interpretation. We are 95% confident that this interval contains mu, the population mean amount of ice cream per carton. But you don't want to write mu in your statement for the layperson. You want to write out what mu means. So as a practical matter, what's some good business advice for the business? Wait, these cartons were labeled 16.0 fluid ounces. What's happening? What is actually happening? Based on our sample results, what does it look like is actually happening? It looks like too much ice cream is going into these cartons. Okay. In fact, notice here, this interval does not contain 16.0 fluid ounces. So if anything, we're very sure that the 16.0 fluid ounces is out of whack. We're pretty confident. We're very, very confident, in fact, that this machine is putting too much ice cream in the cartons on average. So what should the ice cream company do as a practical strategy? Well, the cartons are supposed to contain 16.0 fluid ounces of ice cream, yet the 95% confidence interval here, that's a pretty high confidence level, that's a very high confidence level, does not contain 16.0 fluid ounces. So based on this analysis, the ice cream company has sufficient evidence against the claim that the population mean is actually 16.0 fluid ounces. In the last part of this course, we're going to use a lot of this kind of wording when we do hypothesis tests. The ice cream company has sufficient evidence against the claim that the population mean is 16.0 fluid ounces. Is putting in too much, looks like. So it may want to recalibrate the machine so that it puts less ice cream in the cartons. So the danger for the company is that the company might be wasting ice cream. It might be wasting money in a way because it's putting in too much ice cream into the cartons. They may not get in trouble by the government or from consumer groups, maybe from dieting groups, Weight Watchers, but internally, they may be wasting money because they're putting too much ice cream in the cartons. Next up, what if instead of a 95% confidence interval, we do a 99% confidence interval? And think about it. How will this be different? Next time.